So imagine throwing jagged rocks, hydrofluoric acid,
Yeah.
and like boiling water at a piece of steel 24 hours a day.
Yeah.
How many days until it completely dissolves or shatters?
Oh, easily less than one.
Right.
Yeah.
In harsh environments like mining, if you pick the wrong pump material, the answer is less than one.
Definitely.
So we want to welcome you to this third episode of the podcast, The Pump Zone, presented by Pump Systems Academy, powered by Dynapro pumps. Today, we're doing a deep dive into the intense materials science keeping industrial pumping systems alive.
Yeah, because the stakes here aren't just a minor mistake. We're talking about preventing catastrophic premature failures that cost, well, millions in unscheduled downtime.
Millions? Wow.
Yeah. I mean, pumps look like these indestructible iron beasts, right? But they survive only because of the precise atomic structures of the materials we build them with.
Okay, let's unpack this. Because a pump's environment is so brutal, its first line of defense is its metallic construction. But we're not just talking about generic iron.
Right.
You have standard gray iron, which is
Right.
cheap and absorbs vibration, but it's incredibly vulnerable to impact and corrosion.
It really is.
To understand why, it's like choosing footwear. You wouldn't wear everyday sneakers like gray iron to hike an active volcano like a severe mining application.
No, you definitely wouldn't. Gray iron is great for clean water, but it's basically like hard candy. It's tough, but if you hit it with a hammer,
It just shatters.
it shatters into pieces, which is a nightmare when you're pumping abrasive mining slurry.
Right, of course.
That's exactly why engineers upgrade to nodular or ductile iron for the tougher jobs. The graphite inside ductile iron is spherical rather than flaky.
Spherical. Okay, so what does that actually change?
Well, that structural shift means it behaves more like a heavy-duty plastic. It actually bends and absorbs the impact energy instead of just instantly cracking.
Oh, that makes sense. And then, when you step up to corrosive environments, you need carbon steels for the structural strength and stainless steels like 304, 316, or duplex grades.
Yeah, and even special alloys like Nyhard, Hastelloy, or Monel for extreme abrasion.
Right. But how does changing the alloy actually stop, say, acid from eating the pump?
So it's all about forming what's called a passive layer when you add specific amounts of chromium or molybdenum.
Oh, the specific elements.
Exactly. Those elements react with oxygen to form a microscopic self-healing shield on the metal surface. And that shield stops the corrosive fluid from ever touching the underlying iron.
That is wild. A self-healing shield.
Yeah.
But I mean, even the toughest metallic armor has blind spots. No matter how hard you make that Nyhard or Hastelloy, it can't bend infinitely.
No, it can't.
When a massive jagged rock hits a rigid metallic impeller, that kinetic energy has to go somewhere, right? If the metal can't absorb it, it fails. So how do you give rigid metal the ability to take a punch?
What's fascinating here is that this is the great paradox of material science and pumping. Sometimes the best way to survive the hardest, sharpest rocks isn't to use the hardest metal.
Wait, really? What do you use then?
It's to use the softest rubber. We rely heavily on non-metallic elastomers, which are basically engineered rubbers, for liners and seals.
Oh, because they just bounce the rocks away. They have excellent fine abrasion resistance.
Precisely. They act as literal shock absorbers so the metal doesn't take the physical beating.
That is so clever.
It is. And it's not just physical shocks either. Polymers like PTFE, which most people just know as Teflon.
Oh, right, like in frying pans.
Yeah, exactly like that. They handle the chemical shocks. PTFE is prized for low friction and chemical resistance.
Wow.
Adding those polymers, along with industrial ceramics and coatings, essentially pads the metallic armor from the inside out to boost lifespan.
Okay, so you've got this complex cocktail of ductile iron, elastomers, and PTFE. But practically speaking, if I order a 316 stainless steel replacement part from a brand new supplier halfway across the world,
Right, a very common scenario.
how do you guarantee it won't instantly fail? The sources point to the ASTM, the American Society for Testing and Materials, which dictate chemical composition limits and tensile strength.
Yes, the ASTM standards are crucial here.
But honestly, isn't this just a massive bureaucratic checklist slowing engineers down?
Well, I get why you'd think that, but it's actually the ultimate safety net. It's a legally binding recipe and testing methodology.
A safety net, huh?
Yeah, the ASTM standard limits things like carbon or chromium content, but it also mandates the exact testing procedures.
So how to test it physically.
Exactly, like how to pull the metal apart to test its tensile strength and exactly how to measure its hardness.
Meaning, if a vendor cuts corners, The standard provides the exact physical test that will catch them before the part ever goes into the pump.
You got it. It reduces vendor variability entirely. It guarantees interchangeability and repeatability.
So it creates a universal language of reliability for engineers.
That is a perfect way to put it.
It really takes the guesswork out of the chemistry.
Right.
But, before we wrap up, I want to leave you, our listener, with a final question to ponder.
Go for it.
As extreme as these pumping environments are, how might the actual fluids being pumped continuously interact with and slowly alter the chemical structure of these supposedly stable materials over decades of use?
Oh, wow. That is a phenomenal chemistry problem to leave on.
Right, just something to mull over.
Yeah.
Well, thanks for joining us on this deep dive. Make sure to tune in to the next episode of The Pump Zone, presented by Pump Systems Academy, powered by Dynapro Pumps. Catch you next time.